Hello, hello. Hello, hello. Good afternoon, Yulia. Hello. Yes. Wow. Yes. Hello, Kazi. And yes, I kind of regret that I regret that it's the last class and I regret that it's short. But hello, Marlon. And good afternoon, Adriana. And hello, Kareem. It is good to see you all. And yes, this is our last gasp together. Hello, Shasha. Hello, Cassandra. Good to see you guys. It really is. And yes, I'm a little sad. And I'm always a little bit screaming to try to, make sure we tie up all loose ends. Never did go over homework 3. Okay, anyway. Oh wow, and some people are not here, but okay. It is good to see you. In our 75 minutes, I will try to not get too emotional and I'll try not to get too deep into any one particular thing. I would like to let everybody into the room. Hold on a second. Okay. My main goal here is, that you leave today feeling like when that final exam is posted, which will look very, very much like the thing you already have in your possession, that you'll be able to do it and do it well. My understanding is that you went over a lot, that you went over the Walters part with Walters yesterday, and that you went over a lot of the rest of it with Walters yesterday. Right. Okay, good. Thank you, Kazi. That's what I thought. That's good. Oh, people coming. Hold on. All right. Okay. 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 I'll just pause for a second and get my head together. Yeah, more people. Oh, no, wait, I thought one was here. Okay. Hello, Alex. Hello, hello. All right. Good to see you. All right. So, yes. Okay. That's a good question. And hello. Good afternoon, Noreen. And hello, Al Medina. I guess I was a little early. Sorry about that. Or early for being late. Okay. Wait, the most important. So I'm just pausing for a second while everybody still comes in. The main goal is to finish up whatever we need to regarding the final exam and put together. Yes, it is our last day. I totally agree, Alex. So our goal is to tie up these loose ends from the final exam document. And hello, Fahima, and good afternoon, Diana. And okay, well, this is what we're about to resolve. All right, okay. I'm going to take it. Hello, Charles. Wait, is Charles? Oh, yeah, okay, sorry. Yes, hello, Charles. Sorry, I was confused for a second which section it was in. Okay. Yeah, the main goal is to tie up any loose ends, that any big pieces that were not gone over with Walters yesterday. And yeah, that's our goal. So we'll clarify this right now, like what Shasha is talking about in the chat and what Yulia said in the chat. Okay, so let me get out I think so. Just so that you know, I had a big visit with Professor Walters yesterday and a big talk on the phone. I think I know, like, believe me, our goal is to together make sure you're prepared for sure. So, I think I understand where you got to yesterday, but certainly I want to hear it from you and make sure that all of our stories line up. And just, okay, I'll just say on a personal note too. Well, okay, no, let me get it. Okay, hold on a second. I'm going to get the exam. Hold on. But yes, the goal is to finish whatever was not finished yesterday, or to show you that it's not that big of a deal. So hold on. But now I'm getting myself confused. Sorry, all these windows. When Quark closes a door, he opens Microsoft window. Where did it go? Sorry, I'm just getting out the thing. But yes, okay. Okay. So I'm just looking at what you guys just said. You're saying like Yulia. Okay, I'm going to switch my screens actually, so that we can both be talking about the same thing. Okay. I believe we are talking. All right. So so confusing. Where's the chat? Did I lose the chat? I've lost the chat. Forgive me. The chat. Okay. Went over part 3, part 1 problem today. So Yulia is saying part 1 problem, and Shasha is saying we went up to part 3, question 1. So maybe I'm going to ask again. I had a plan. I thought I knew what it was that you hadn't gone to, but maybe I'm confused. So can either Yulia or Shasha or both elaborate where it, like, okay, more people are coming.
I think for this part, this page we did the whole thing, and the next page I think we didn't do only the last two, X, Y, I think it was.
Oh, okay, okay.
I think we didn't do the last two only, and the first or the last three, I'm not sure, 2 or 3. Yeah, and the part 1 we didn't do in class of the exam review.
Part 1.
Part I. Wait, were you talking about one from the part 1 or part I of like part 3?
I'm talking about part 1. I really want to go over that one.
The Doppler effect one?
Yeah, the first one. It's on the first page. Yeah.
Okay. Okay.
And then a part 3, I think it was the last 2 that we didn't get a chance to go over. Yeah.
The last. Oh, okay. Oh, so X, Y, and possibly P on this page that I'm looking at right now. You're saying, so are you guys saying, so X and Y you definitely did not go over, and you're saying, right, X and Y you didn't go over, and but you went over all the ones before that, like you went over this whole page here?
Yes.
Yes, okay, including I, the very last one on that page.
Y and P at the end, 2 last problems for this part. Y and P.
Yeah, but I just want to make sure, just bear with me. On this page right here, where it says W and then Z and then I, you literally did go over all 3 of those, you're saying?
Yes.
Okay, great, great. Okay, fantastic. So your concerns are X, Y, and P on this page, X, Y, and P on this page, and then the number 1 all the way here on this page. Am I correct? Is that what we're saying?
Yeah, I think so.
Because I think I can do that. I don't mean to take too much time right now, but if that's what if especially if people are agreeing, if like Shasha and Yulia and Kazi, if you're all kind of saying that that's true, that you'd want to see. Oh,
yeah, that is true. I mean, we didn't go over part 4 and 5, but it's like arranging them in the order. I think we should be good with that.
Yeah. Like, no, and you're right. And honestly, there's no way, and we never intended to be able to walk you through every single bit of the whole thing. I mean, you're right. But I also agree. I appreciate that you want like some exposure or some, like it's true. Each one of these letter things, you have to pass through more than once. First you say true, false, then you have to do the numerical problem. And you're right, we're not going to do every single stage of that. But if what you're saying is that Walter's got to say something about every bit except for this X, Y, and P, then I am happy to say something about X, Y, and P. Like, I think if that would be the missing piece to be consistent, I'm happy, I think, to talk about X, Y, and P. And And then number one on the first page, I'll try by the end. But the truth is that one we spent, I'll try by the end, but I think we have a lot of notes on that. And I might, well, we'll see. I'll see what I say by the end, but I won't do that one first, just because I think we do have a lot of notes on that. And maybe I might, maybe we'll see what happens with that. But let me just look in the chat. But is there anything else big? If those are the things, I mean, I can do that this period, and that's good. I mean, that makes sense to me. Let me just see what's happening in the chat. Oh, wait, oh, yeah, no problem. Oh, okay, wait, okay. Hold on, just. Right, no, and I understand you didn't do 4, 5, and 6. Okay, oh, sorry, I'm just thinking for a second. Okay, let me just think. I'm looking at all these questions in the chat. Let me just think for a second. Sorry. Okay. Okay. Here's what I think we're going to do. Today's Wednesday. We said the final is going to be due next week, right? I mean, the final is going to be posted next week. So I want to answer Hannah's question. And I think here's what I think. I think this will address both Hannah's question and what everybody's saying, what Shasha is saying. And here's what we're going to say right now. I'll try to put this in Google Classroom, but I'm going to just say it right now and tell me if you hear me, and then I will put it officially in Google Classroom. Part 1. Okay, I know I keep saying it's super important and all that, like it is, but also we've literally done this problem, in fact, more than once in a way, in class notes, in the class period. I'm not saying that in an admonishing way, but I'm saying I definitely know that you all have notes on a problem like this, just with slightly different numbers, and you have at least one video on it. Therefore, here's what I'm going to say. I'm going to say right now that part 1, the thing that's on the screen right now, the I'll wait. I know someone's joining. Hold on. I'm just going to say this slowly and clearly. Okay. Part 1, the thing that's on the screen now, especially just in case I don't get time to walk it through today, because I'm very confident that you have notes on it and a video on it, I'm going to say that is the extra credit. Okay. That this thing right here, part 1, is extra credit for, like, so you don't have to do it all if you don't want to. It's not part of the actual final, just this part. And again, I'll try to make this clear in Google Classroom, but like, please hear me now. I'm saying if you just turn in a full solution to this thing, let's say by Monday of next week, again, obviously I'm making this up right now, but like, let's make this real. If you turn in just this problem nicely with a diagram and everything, just try to make it as clear and thorough and comprehensible and comprehensive as possible. Just this part 1, this ABC thing here. Turn a solution of that in. I'll make a portal for it and everything, but I'm just preparing you to say, if you turn that in by Monday of next week, that's the 13th, that will be for extra credit. That will be like for like a lot of extra credit. And I will grade it generously. And of course you can work together and all that, but just show that you really get what you're doing. Take it seriously, make nice diagrams. It's a small, I'm not saying it's easy, but it's somewhat small and contained and simple. So I think it's a perfect answer to Hannah's question. Honestly, I think it's perfect because I've been promising that you would have some extra credit opportunity to like lock in your grade even before you take the final. So I actually think this is a perfect right here. If you just do this part 1 optionally and turn it in for Monday, nicely with your name on it and all that, I will give you, like, I'll count it out of 100. I'll make it worth, I can't say I'll count as a full freaking exam grade, but I will count it for a lot of points, and you'll have that cushion going into your final exam. Okay. And again, I will try to make this clear in the Google Classroom, but all right, wait, I'm seeing chat, and I will ask you if you oh, great. Oh, Oh, great. Okay. I didn't expect that. Oh, great. Okay. Okay. Wait. And I do see that Kazi has her hand up. So hold on one second. But I want to say thank you to you. I was about to ask it. So I'm gathering from your thank yous that that's clear and that you appreciate. Good. If you appreciate it, I appreciate it. But now, okay, Kazi, go. So, oh, I think
I
you
have a question regarding solving part one and the final in general.
Okay.
When we're doing it, do you want us to use like DFP, WIQ, GDP, all that?
Oh, that's a great question. That's a great question. Where I really want that, great question. Where I'd love to see that the most is when you're going through part, I think it's part 4, when you actually go through and try to answer these fragmentary questions in the computational way. So I think it's part 4. Let me scroll. Yeah, part 4, where it says like, if T add one more electron to same location and calculate E field, if false, correct. So these are like little problems here. That's where I would most like to see you do that, like WIQ. Yeah, that would be great. And to everybody, let me see. So what she's talking about, what Kazi's talking about, is that 5-step method for solving problems that I highly recommended and tried to teach at the beginning of the course. And let me say to everybody again, I'm glad Kazi asked. I think this might have come up before. Even that is not a requirement. I'm not saying that you could possibly get all the credit if you don't do exactly that way. But if you try to do it that way, it's a really smart thing to do, because first of all, I will see that and be very inclined to grade very generously if you do that, if you just spell out your work in that way. And then just in case you do make mistakes or you don't get a right answer or something, you'll get so much more partial credit for doing all that. It will really cushion your grade. The more you can show me that you not only understand what you're doing in these problems, but you sort of have gotten something out of this course and see how to do physics problems in this course, the better. So yes, to Kazi's question, I would highly recommend or request that you try to do that 5-step solution method for part 4. I'm also, okay, and you know, and that includes making diagrams and so forth, where you can really strut your stuff and show that you know what's going on, is in part 4. Let me also say to everybody, oh, great. Oh, thank you. Oh, great, great. Oh, I love you guys. Oh my God. Oh, did I say that? I mean that in a electron kind of way. But no, thank you. And I'm glad that you hear me. Okay. And so on the Kazi thing too, I mean, on this Kazi, or there too, like in this extra credit that you'll submit for Monday on just that part 1. And let me also make clear again, that will now become the extra credit. That's the answer to Hannah's question, who's been very patient waiting for this forever. And it means for those of you who decide not to do extra credit, you don't have to do that part. Like hopefully, again, I'll hopefully make this clear in Google Classroom, but when you go to sit and do your actual final exam, you don't have to do that part unless you had done it for extra credit. But what I want to say to everybody now, since we have limited time together, is it is clear to me. I do get, like, I think Walter's went over a lot with you. I think it's great. And hopefully we all are going to go into this with very little sense of mystery. I totally understand that Walter's did not walk through part 4 with you. Like, I know that. And honestly, that we never expected that he would. And I'm not going to be able to walk through part 4 with you today. In other words, the one thing you're not getting from us is like sort of the final answers to these numerical problems. So that's really probably where you're going to put the most work in a way over the next couple of weeks. Please remember, we're not going to change these questions or anything because we're not even giving you the answers. I mean, you might find if you go to old videos and stuff or old documents, God bless you. I mean, go for it. But excuse me. But we're not going to change these questions because we didn't even because we're expecting that you are going to try to solve them, that you should help each other try to get solutions to these questions. You should know that we know that part 4 is where you're doing your thing. Like we're not walking through it, you're walking through it. So that's where you, again, just to reinforce the answer to Kazi's question, that's where the more you can show that you are attempting to walk through the steps of comprehension, the more work you show in part 4, the better we'll all be. Because it is possible that when you sit down to do it with one another, you might think, oh, this is a little harder than I thought, or, oh, I'm not totally confident in this answer. That's okay. As long as you're showing all the work and stuff, you'll still get tons of points, okay? So, and it's also, I'm saying, when we end today, I'm sure once I get rolling up, the clock will, ring before I want it to. When we all disappear and go our separate ways at 5:45, and then you come back and text, oh, let me remind you one more time, remember, When we go our separate ways, or maybe you eventually text me for a letter of recommendation or whatever, like we talked about, I think we talked about, you are gonna have to do some work to put this thing together. I'm here to give you the basic, remind you of the basic concept behind each question and what it's looking for and how to solve it. So that's what I'm going to do in a minute. So I think you have focused me properly. Like, I think you are right. I mean, it was my impression from authors that X, Y, and P on this page is the one that, like, sort of, it sounds like nothing has been said about. So I'll try to say right now. But then from there, I think you're in a position, it's not like you'll have every answer in front of you. You'll have every concept in front of you to do this. And please help each other. That's our biggest, that is not cheating. That is our biggest fantasy. And please always remember you've been denied the opportunity to collaborate the way you really would get to if we were all on campus together in the normal fashion. So any collaborating you do it's not cheating. But anyway, okay. So I'm looking now at question X on the sheet. A galaxy known as galaxy norm is a typical representative galaxy approximately 75 megaparsecs away from Earth. Okay, I'm trying to think if I should switch screens or not. All right, at some point I'm going to switch screens to like write things out, but all right. But just reading out loud, it is generally known to recede from Earth at an average speed of 900 kilometers per second. Recently, a distant region called galaxy mad far away was discovered to sit at approximately 310 megaparsecs away from Earth. Consistent with our general understanding of trends in outer space and time, the recession speed of galaxy mad far away is found to be 450 kilometers per second. Okay, what the heck is going on in this question? Fair question. Okay, let me look in the chat. I'm sorry. Oh, wait, okay. That's a great question. Spoken like a true City College student. So, okay, sorry. Kazi's question in the thing, if we get help from others, should we say, for example, Noreen, help me to understand, blah, blah, blah. Very fair question. And in a lot of circumstances, academically, of course, you're supposed to do that. And I'm a big believer in that in a lot of contexts, but I'm going to tell you all right now here. I mean, if you want to do that, to give your friend credit and stuff, or just to let me know so that I can be happy that you collaborated, sure you can. And don't forget, by the way, that, there is that multiplayer co-op assignment portal that you can still, if you remember, you can still put things in. Like, I love it when any of you do acknowledge each other's existence and cooperate with each other, and let alone when you then acknowledge to me that that's happened. I'm all for that. But I got to tell you, truthfully, in your exam, you do not have to do that. You don't have to. And I will tell you why. There's a whole discussion unto itself, but the truth of the matter is, what we are looking to see you do in the final exam is prove that you understand what you're saying. So what you don't want to do in your final exam is just write down correct answers and expect them to speak for themselves. I mean, not in part 4 anyway, you don't. What you do want to do is show comprehensive, thorough, step-by-step work to show that you really understand each solution. Here is the reality, is that the more steps you show and the more you attempt to actually break down a solution into a process and show that process, the more we can tell whether you actually understand what you're writing or not. And the reality is, it's nice if you tell us how you got help and stuff, but I don't care I care, but as an ethical question, as far as like cheating or plagiarism and stuff like that is concerned, each one of you can get help right up until the last minute from each one of the others of you. And you don't have to give credit to that help, because you're not claiming in this exam, this isn't a matter. I'm getting all excited because it's a very fair question, but like the point is that what would be cheating in this exam, would be to write down something that even as you're writing it down, you don't understand. And the truth is, we can tell more than you think. We can tell when people do that. And even if they say, I got help from Hannah 2 days ago on this, even if they say that, if they just write down the final formulas that Hannah gave them, I don't care whether they're admitting that Hannah, I'm just using Hannah as an example. I don't care whether they're admitting that someone helped them 2 days ago. As far as I'm concerned, if they just then write down the formulas, then they weren't helped enough and they still don't understand the formulas. Like, it's not, you can get whatever help you want to get you to understand, But then by the time you get to the piece of paper, what you're trying to prove to me is that what you actually write down in that moment, you actually now understand. So all the help in the world yesterday is fantastic, but you don't even have to credit that person. It will become your work and your understanding and not cheating if what you're demonstrating is comprehension, which you can only do by actually breaking things down into lots of steps or adding your like personal touch. Like we can really tell the more steps people add, the more they start showing with their different colors or their diagrams or the way, I mean, you'd be amazed. It's okay. I'm going to say this quickly. We've probably said it before, but honestly, to all of you guys, many of you speak another language besides English, whether it's your first or your second language. Just think about if we were giving you a test in any other language, like for some of you, maybe like your native language, or if you study Spanish, even if that's not your native language, if we were giving you a test in Spanish and the final exam was like, write down what you did for your summer vacation, like write an essay. Walters has probably said this before, but it's so true. If we asked you to tell us what you did for your summer vacation in Spanish, okay, like, we can tell the difference. My analogy is falling apart. You know in your heart that if you actually speak Spanish, you could and know Spanish, you could write that essay in Spanish. But if you don't actually get Spanish, you could try to copy all these words and copy all of these sentences, and you could try to copy all of this stuff from the web and things. But if you copied a bunch of fragments and tried to put them together, it would not flow like an actual native speaker. It would be obvious, or even better, like Arabic. If there's some Arabic essay on the web and you just tried to copy the Arabic and submit it into our test, but you didn't even know Arabic symbols and you just tried to copy it, it would be, if we do speak Arabic and write Arabic and read Arabic, it would be so obvious to us that you just copied and that you didn't know what you were saying. That's what physics and math are actually like. We're saying the truth is, if you just write things down because they're supposedly correct, even if you write lines and lines down that you got from someone else, it's much more obvious than you might imagine when people are just copying things than if they actually get what's going on and are breaking it down for us. So what we're really, I don't mean to get off on a tear about this. I'm very, very happy and impressed that Kazi would ask that. But what I'm really here to tell you all is get as much help as you can and need, as long as you know in your hearts that you're getting help to understand, that you're getting help so that by the time you sit down, you can confidently write out things and break them out for us. And as long as you do that, you don't have to tell us who helped you. Conversely, even if you do tell us who helped you, if they didn't help you enough, it won't matter. You're cheating if you write down things that you don't understand, and you're not cheating if you write down things that you understand, whether you made them up or not. None of us is making up physics. We're just trying to understand it. All right, it's a long answer, but I think you get it. But I'm glad she asked. I'm going to go back to the thing now. Okay, sorry. I just get all excited. I just blah, 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 blah. All right. Some of the, okay, anyway. Sorry, I'm just, okay. All right, so this question about the galaxies, galaxy norm and galaxy mad far away, whatever. What is this really about? What type of question is this? This is about one of the last things we ever discussed just last week. This is about Hubble's law. I would like to, I'll probably switch screens in a moment, but until I do, well, I think I can do that. Well, this is about, I'll try to, I don't know how this appears on your side, but this business that we're talking about right here, I think I have mentioned this before. I think I even remember somehow writing this into it, but this is about Hubble's law. This is about the idea that the farther away a galaxy is, D, from us, the faster rate at which it will move away from us. This is our way of, this is the mathematical way of expressing the expansion of the universe. H is just a constant. I'll try to write that. Can you see on your, oh, okay, I can't see. Yeah, you can, okay. And I apologize, I always spell Hubble's wrong, no matter what I do. Even when I know I'm spelling it wrong and I change it, it's still wrong. So
You spelled it the same way as the last one.
And it's not right, right? Or is it right? I don't know.
It's not.
It's LE. Golly, I don't know what. All right, it's LE. Well,
It's okay. It's okay. It's
all right,
fine.
thank you. All right. See, if you're not a native English speaker, you can tell. All right, anyway, I'm okay. It is. What am I? Oh, it is. Okay. We're saying the farther away something is, a galaxy is, the faster it moves away from us. That's like the statement here. That's what we want you to know. So it's just like if you were to make a graph of velocity as a function of distance, it would be a straight line graph, and the slope of that straight line graph would be would be h, what we call Hubble's constant. Now, Hubble's constant is measured in kilometers per second, i.e., of velocity, kilometers per second per megaparsec. Oh my God, like what is a megaparsec? Okay, I'm going to write that. I may have to add another text box. I mean, that sounds almost intimidating. It's actually just a cool piece of knowledge, and to make that sense. It's a unit of distance. Let me put it that way. A megaparsec is an enormous unit of distance. So we're just saying that the farther distance away you are, measured in this thing called megaparsecs, the faster you should be moving away if you are a galaxy. Just to be clear, one parsec is approximately for a little bit less than 4 light years. A light year is the amount of distance light travels in 1 year. So I'm going to write that down too. Well, or in other words, speed of light is approximately, and this is sort of like, okay, the speed of light is approximately 3 times 10 to the 8th meters per second, or 3 times 5 kilometers per second, 300 million meters per second. That's very fast. That's like 186,000 miles per second. I mean, I'll try to put that in perspective by the end of our 45 minutes, but so a light year is how far light travels in a year. Light travels about 300 million kilometers in a second. There are approximately 3.15 times 10 to the 7th seconds in a year. I mean, you could, in other words, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. So a light year is an enormous number of kilometers. You can figure it out based on these facts. It's in the quadrillions of meters. A parsec is about 3 of those. There's a reason that a parsec is a standard unit of astronomical distance, and we use parsecs rather than light years for a number of reasons. But one way to know it is just like the star that is closest to us, of all the stars that could ever be seen from Earth, other than the sun, of all the stars that are ever seen in the night sky of Earth, the one that is the closest to us is a star called Alpha Centauri. Now, we don't generally even see that from New York or from the Northern Hemisphere. The truth is, to see Alpha Centauri, you really have to go to like Australia or New Zealand, whatever. But it is the star that is closest to us other than the sun. And that star is a little bit less than 4 light years away. So that becomes, there's other reasons, but so that distance between it and us is kind of like the yardstick that we use when we're measuring distances on the scale of the universe. Okay, that's all kind of detail, but the point is that this problem then, we're looking at whether it's true or false, right? I'm trying to, okay. All right, so we've got this one galaxy norm that's 75 megaparsecs away from Earth. Apparently, it's generally receding at like 900 kilometers per second. Okay, so there's a distance and there's a speed. Then we have this other galaxy that's even way farther away. That that's apparently 310 megaparsecs away from Earth. So it's much farther away than galaxy norm. But the assertion here is that it's receding at a speed of 450 kilometers per second. To cut finally to the chase, what I want to say is this one X is false. It is false because a galaxy much farther away should be moving much faster than a galaxy closer to us. If we understand Hubble's law, the idea is that the farther away things are, the faster they're moving. And in fact, it should be directly proportional. So I'm not at the risk of giving anything away. Like this one's false. I'm saying it's false. It's about Hubble's law. It's false. Things farther away should be moving faster than things closer. And according to Hubble's law, they should be moving in a directly proportional way. So if this other galaxy is about 4 times as far away as the closer galaxy, it should be moving about 4 times as fast, not 1/2 as slow. Okay, so I don't even remember what the question asks you to calculate later in part 4, but if it asks you to calculate, you can use Hubble's law to calculate. And the truth is you don't even need to literally know the constant, even though I just gave it. I mean, you don't need to know the constant. You just need to know the idea that the proportionality is direct. Okay, so that's it for that one. Is it any, I'm going to move on. Okay, I'm going to, now I don't know how to get rid of these annotations. Can I get rid of these annotations? I don't know. This is all getting so confusing. Yeah, I don't know if I can get rid of these annotations, sorry, but, oh, clear all my drawings. Okay. Oh, it just clear. I'm sorry. Yeah, oh yeah, on Sasha's thing, hold on a second, sorry, 1 second, let me just clear viewer drawings. Okay, why didn't that? Oh, I don't know. On Sasha's question, for the true false part of this exam, you do not need further calculations at all. For good or for bad, you don't even, honestly, on the true false part, yes, it's totally sufficient to just say because of Hubble's law. You're going to strut your stuff calculation wise in that part 4 part. So you don't have to say anything further here. You do not need further calculations for here in this part. So great. And I'm okay. I don't know why. Well, okay. So let me go on to the next. Sorry, I'm just trying to. Okay, so then the next question. So that was a Hubble's law one. Gunther's a famous, so now why? Gunther is a famous lion tamer. He's famous for surviving the, okay, that's stupid. Oh, all right, so now this is about waves. The equation that this is about, okay, yes, this is about, let me, at the risk of, again, of messing up your screen, what this is about I'll say this. Okay, this is about V equals lambda times F, this Y question. And the important part here, before I say true or false, the important part is for any wave, the speed of the wave relative to the medium is constant and cannot be altered. Like that's the big takeaway we sort of got to when we did waves for a lot of the semester. Once you generate a wave, the speed of it relative to the medium, there's nothing you could do about it. It's fixed by physical properties of the medium, fixed by parameters. So the speed of a wave, V, is a constant. Speed equals wavelength times frequency. So you can control the frequency of a wave. You can increase the frequency, but thereby necessarily you will decrease the wavelength. Or you could decrease the frequency and necessarily you will increase the wavelength. The wavelength and the frequency are inversely proportional to each other because wave speed is necessarily constant. for a wave relative to mean. Therefore, as long as I'm reading this correctly, let me just read it one more time to make sure. Yeah, so this is true. This one is true. Y is true. And it's like very, very true. Like it's exactly right. Like if you are trying to make wave ripples go along a string and you like shake faster and faster, you might think that you might be trying to make those ripples propagate more rapidly along the string, but you will fail to do that. You cannot control or influence the propagation speed of a wave. If you move your hand more rapidly and generate a higher frequency wave, what will happen is the wavelength will adjust in order to maintain that same speed. The wavelength will go down if your frequency went up. And if your frequency literally doubled, then your wavelength will literally go down by a factor of 2. It will become half as big. They are inversely proportional. So like Gunther might be trying to do that, but Gunther will find exactly what this thing says. So it's true. So Y is true. Okay, are we good? Can I just get comfort? Are we? Oh, okay. Thank you, Shaka. That's awesome. Thank you. I love the thumb. Okay. Okay. I totally love your avatar too. Okay. Anyway. All right. So now P. Am I doing P? Yeah. And then we're good. Okay. P. Okay. A mass is at one end of a well-behaved spring. Can you read? Oh, you can't read. Why? Wait a minute. Oh, okay. Okay. Sorry. A mass is at one end of a well-behaved harmonic spring. It oscillates back and forth between position -6 meters and 6 meters. Each full cycle takes approximately 4 seconds. The process is interrupted and has begun later with the same equipment. This trial, nothing has changed except that the same mass is released at t equals 0 from position 3 and so oscillates. Oh, okay. Oh, okay, okay, okay. This is interesting. Okay. Okay. First of all, cut to the chase. This one is true. I probably should ask you guys to, but anyway, this one is true. This one is true. And again, it's sort of interesting, kind of like why it's true, because, and it's truly saying something that might be slightly surprising or unexpected or counterintuitive, but it is the real true point. So let me break it down, yo. What it's really getting at here, it's really getting at two things. One thing is it's getting at is that frequency of a harmonic oscillator is independent of amplitude, that frequency is determined by parameters, not by conditions, that the rate at which a harmonic oscillator goes back and forth is determined entirely by the physical properties of that oscillator, such as mass and stiffness. It is not determined by initial position or initial configuration. The amount of time it takes something to go back and forth is not determined by the amount of space that you initially give it to go back and forth. So first of all, what it's really saying is, even if you change the amplitude of an oscillator, even if initially you let it go from 6 meters and let it go back and forth between 6 and -6, and then you let it go from 3 meters and let it go back and forth, no matter what, it's going to take the same amount of time to go back and forth, which means that the one with the smaller amplitude on average is going to be going slower than the one with higher. I mean, this all brings us back to the beginning of the semester. The one with higher amplitude on average is going to be going a lot faster to cover that greater space than the smaller amplitude one. How does that work, or why does that work? Because the original higher amplitude one that you released from 6 meters, well, you're originally giving it, by releasing it from 6 meters, it has a lot of potential energy when you, like 1/2 kx squared, when you release it from 6 meters. So on average, and energy is conserved in a harmonic oscillator. So on average, it's going to have a lot more kinetic energy than the small potential energy, small kinetic energy one. So the one that has to go a lot farther will on average go a lot faster. And it turns out by exactly the same amount. So the period/frequency of both of these oscillators is the same, even though we change the amplitude. Frequency/period is independent of amplitude. That's the main point. But let me say one other thing. This also requires that you're sort of comfortable and casual in your brain going back and forth between frequency and period, the way I sort of just was. In other words, it says in the third line, each full cycle takes approximately 4 seconds. What it's telling you is the period. It's saying the period, the amount of time for a full cycle is 4 seconds. Then it sort of shifts its language. It's a little bit tricky. It sort of shifts its language at the end and says the frequency on the second oscillator is approximately 1/4 cycle per second, 1/4 of a hertz. That's a different way of saying what is ultimately the same thing. We are expecting you here to be able to realize that, to realize, let me write it in. We are saying here, we're asking you to realize that period and frequency are reciprocals of each other, and, and therefore also, right? So something that takes 4 seconds to do a cycle does 1/4 of a cycle per second. That's 2 different ways of saying the exact same number. And the number of the frequency should not have changed, just even though the amplitude changed. That is true. So that's P. So let me just, I'm going to pause for a second. Okay. So first of all, is that good? Are we sort of clear? Whoa, did I just, I have no idea what's going on, but are we clear? Oh my God. I'm trying to get back to my speed, but is this good? Are we clear so far? Could I get any? Okay. Thank you, Julia. All right. Awesome. Awesome. Okay. Awesome. Thank you, Quan. I totally appreciate it. Thank you. So, okay. Can I ask, chat. Oh, too fast. Okay, sorry. I'm happy to slow down. Which on P? Would you like me to say more about P? Shasha? Okay, P. Well, let me think for a second how to say this better. Well, one thing here, this might help a little bit. Okay. Oh, about the period and frequency. Oh, okay, sure. Well, partly what I'm saying is up here. I don't know if you could see this. Oh, you can see. Okay, this T equals 1/f, F equals 1/t. What I'm trying to say there is that period and frequency are always inverses of each other. So what I'm saying is if, and this is an always thing, if, here, I have a way of saying it. Hold on, I'll try to write this. I think okay, if we think about this in terms of units, I'll move this over. If we think in terms of units, period is the number of seconds it takes you to do a cycle, and it's literally measured in seconds per cycle. Frequency is the number of cycles that you undergo per every second, and it's literally measured in cycles per second. Although a name for a cycle per second is a hertz. 1 hertz means 1 cycle per second, but frequency is measured in cycles per second. Period is measured in seconds per cycle. I'm saying that they are therefore reciprocals of each other. If it takes you 4 seconds to do a cycle, then that means if it takes you 4 seconds to do a cycle, that means that when 1 second has elapsed, you've only completed 1/4 of the cycle. If it takes you 4 seconds to do 1 cycle, then you're doing 1/4 of a cycle every second. So period and frequency are the opposites of each other, the inverses, the reciprocals. And therefore, in this problem, when it first says each full cycle takes approximately 4 seconds, but then it says at the end of the problem, this time the frequency is approximately 1/4 of a cycle per second. What I'm saying is that's really two different ways of saying the same information, that the rate of this thing apparently has not changed. We're just expressing it two different ways. And that's as it should be, because the real point of this is if you change the amplitude of a harmonic oscillator, that should not change its frequency rate or its period rate. No matter how you say frequency or period, the frequency or period, the rate of cycles in time, or the rate of time in cycles, that should not be changed, even though you change the amplitude. And that's what's happening here. Does that make any sense? Does that help at all? Oh, chat. Okay, so. Oh, okay, cool. Thank you. That's awesome. I love this class. Don't tell anybody. Don't tell anybody. Okay. I'm gonna miss you. Don't tell anybody. Okay. Who said physics wasn't personal? I don't know who said that, but they were wrong. Okay. Okay. Oh, so P. Wait, no. So P is true. P is actually true, because I'm glad you're asking. I'm glad we're getting this clear. I'm saying, and maybe someone correct me if I'm misreading something or something, or if I'm being confusing, but I'm saying P is true because I'm saying what I'm really, wait, X is false. P is true. Yeah, I'm saying X is false, Y is true, and P is true. That is what I'm saying. And I'm saying P is true because I'm saying that a period of 4 seconds is the same thing as a frequency of 1/4 cycle per second. So I'm saying that in this whole paragraph of P, the frequency never actually changed. They're giving you the same number expressed with two different ways or two different equations. The frequency never changed. And I believe that that is correct. It shouldn't have, because nothing, it says, it says, nothing has changed in this trial except that the same mass is released from the position 3 meters instead of 6 meters. Like the only thing they changed in this oscillator was amplitude. And the real lesson or the real concept here is that amplitude should not affect frequency or period. Like going all the way back to this chapter in the course, like omega, if you remember, equals square root of k over m. For example, omega equaled square root of k over m. It got determined by stiffness and mass. Omega, angular frequency, never got determined by anything about the amplitude. There's no x naught in the expression for omega. So even though we changed x naught here, that should not change the frequency. That's what I'm saying P is actually true. Let me just look in the chat and see if I'm confusing you. Oh, okay, cool. Okay, so yeah, so cool. Okay, but I love that you guys, okay, cool. So yeah, okay, all right. So that's, and again, you could still submit all these things for points. Remember in the portals. Okay. Chat. Oh, great question. Now, if the mass had changed, then that would change the frequency. You are correct, Shasha. If the mass had changed or the stiffness of the spring had changed, that would change the frequency. Yes, that's right. And okay. And to everybody then, that almost then brings us back to Y, or brings us full circle or toward the end of the course, because what we're really trying to say here, what we're really trying to say in P is that the rate at which a harmonic oscillator oscillates is not determined by how you set it up. It's determined by the materials it's made of. That's what we're really trying to say. We're trying to say that oscillation rate, oscillation frequency is determined by parameters, not conditions. It's determined by like mass and stiffness, not by how you set it up or how much you stretch it. Now, who cares? Like, why is that such a big deal? Well, partly because to send a wave pulse through a medium, what we do is we set up lots and lots of oscillators next to each other. We make one thing oscillate over here, and then another thing oscillate over here, and then another thing oscillate over here. And as long as they all oscillate in a patterned way, as long as we stagger, as long as they're all made of the same material, and as long as they're all made of the same material, okay. As long as they're all made of the same material, then and we stagger their phases appropriately by having this oscillate and then this oscillate and this oscillate, we send a pulse through that material. That's called a wave pulse. Like what propagation through a medium, how do we create propagation of waves through media is we set up huge, enormous collections of phase staggered oscillators. What a medium for a wave is a collection of harmonic oscillators. And if we believe that each oscillator will vibrate at a rate that's fully determined by what it's made of and nothing else, that it doesn't matter how you flick it, it's going to oscillate at a certain rate, then what that means is that the wave pulse will propagate through the medium at a rate that's fully determined by what all these oscillators are made of. Because we believe that oscillation rate is fully determined by parameters, then we believe that propagation rate is fully determined by parameters, i.e. the rate at which a wave pulse propagates through a medium is fully determined by the physical properties of that medium. V of a wave is fixed by the properties of the medium for that wave. So no matter how quickly you try to generate the wave, or even if you try to run while you send the wave, or you run back, or you run to receive the wave, you cannot change the rate at which that wave propagates through the medium. It's entirely determined by the oscillation rates, which are entirely determined by the material properties of the medium, such as mass or stiffness. So first of all, that's partly why what's going on in part Y, question the gum through the line type of thing, but also it's why waves travel at such steady, reliable speeds through their media. That, okay, now, and that's why we can trust in this whole Doppler effect thing. We could say, aha, if a wave has to travel at a certain speed through its medium, and so I'm going to chart, now I have 15 minutes. So here I go. I'm about to wrap up the whole course. You'll have to just, I don't know where exactly which question, everything I say now is going to apply to all the questions. Okay. You can flip through while I'm talking, or you can sit back and relax or whatever. But what I'm going to say now is my last attempt and hope to put this all together for you and show you the point of the final exam. What we're saying here, we studied harmonic oscillation at the beginning of the course, and we studied it in one of the big lessons that we were supposed to get from all the math of simple harmonic oscillation is that the rate of oscillation of a harmonic oscillator is fully determined by its physical properties, not determined by what you do to it, determined by what it is, right? Not determined by how much you stretch it, just determined by its stretchiness and its mass. So then we put a bunch of oscillators together and we call that a medium. We put a bunch of like springs next to each other, or maybe atomic springs, or like water molecular springs. We put a bunch of things next to each other that can oscillate harmonically, and we set them off in motion. So we have oscillation, 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 oscillation. Well, what that results in is a pulse propagating through that medium that now we believe, and again, remember what a pulse is. Remember what's fabulous about wave motion is when a wave pulse propagates from me to you, no individual thing moves from me to you, right? So for example, we take a bunch of air molecules and we let each little air molecule over here oscillate, and then an air molecule over there oscillate, or maybe more realistically, a little air molecule over here oscillates, and then an air molecule over here oscillates, and then an air molecule here oscillates. And next thing you know, a pulse has gone through the air from me to you, and we call that pulse sound. And it's fabulous because number one, it means I can send this information to you without actually sending an object to you, right? Oh, chat, sorry. Yes. Wait, the length of the string. Oh, wait, sorry. For a pendulum, sorry, great question, Shasha. For a pendulum, the length of the string and the gravitational acceleration. Well, for a pendulum, mass doesn't even affect frequency because remember, a pendulum is something that's falling, and it turns out that all objects fall at the same rate. I mean, all masses fall at the same rate. So even the mass won't affect the falling rate, but the falling rate does matter. So for a mass on a spring, omega is square root of k over m. For a mass on a string, on a pendulum, omega is square root of g over L. Like mass and stiffness determine frequency for a spring system, and L and G, lowercase g, that 9.8 number, determine frequency for a pendulum. And it's all right whether you say frequency or period. You're right either way, but it's actually string and lowercase g. Yeah. Right. Oh, exactly what Kazi said. Right. Good. Yes. So yes, and thank you, and good question, and good answer, and yes. So, okay, I'm going to assume that's cool, right? I'm going to just go back to this 14 minutes. Okay, so now, why do we love waves? We love waves, well, partly because they're just cool. Because when I send a sound wave to you, remember, like if I send the note A to your ear, I'm sending some kind of information to your ear. Specifically, I'm sending like a frequency of 440 hertz. I'm sending some kind of number to your ear. And in order to do it, I need this collection of air molecules, each to oscillate in a certain kind of a way. So I need air. I need a whole collection of air molecules, and we call that the medium. We need all the air molecules to move in a certain kind of a way in order for sound to propagate from me to you. But even though we need the air to be moving in a certain kind of way in order for sound to move from me to you, please note, and please always remember, no individual air molecule ever travels from me to you, right? So a wave is like this immaterial type of motion that occurs through a medium. So first of all, it's just cool and interesting. But then second of all, what we know about the wave is it is a pulse through a medium that is the net result of a huge collection of individual oscillations. The medium is the collection of oscillating things. So if all the oscillations only occur at a certain rate that is determined by the physical properties of that medium, then the propagation will occur at a certain rate determined by the properties of the medium. Therefore, we can confidently say, once we have a wave, we could say, oh, we expect that wave to travel at a certain speed relative to its medium. And there's nothing that anybody can do to change that speed, even if they move through the medium while they're sending the wave, or even if they move through the medium while they're receiving the wave will move at one and only one speed relative to the medium, no matter what. So we observe this thing called the Doppler effect in waves such as sound, where because of this fact that I just said, because the speed of a wave is so reliable and so fixed and so constant relative to its medium, that means that if either a source or a receiver of a wave is ever moving relative to the medium, then if the source and the receiver are moving at two different speeds relative to the medium, then they will observe two different speeds of the wave, and thereby they will observe and measure two different frequencies of that wave. The wave is going to do whatever the wave is going to do relative to the medium. So if you run into the medium while the wave's coming at you, you're going to encounter the wave ripples much more frequently than if you stood still in the medium. So there's this thing called the Doppler effect, which when we think about it with sound, what we find is, oh, when things are, for example, when something is making a sound, when something is sending a sound to us while it's moving away from us, will receive a sound frequency that's much lower than the sound frequency than they sent if they're moving away from us. And that's what you're being asked to practice or remind or review in the part one, which is now extra credit, portion of the test. Again, just do it and just do it by Monday and you get tons of extra credit for it. You're being just asked to practice that idea that if there's any kind of motion between a source and a receiver of a wave, then there will be disagreement over the frequency of that wave. Now, right? So for example, if someone making a sound was running away from me while they sent that sound toward me, I would experience, I would measure those sound waves less frequently than, than the source would right? So, and that's what you, right? So the frequency of received wave would be lower than the frequency of the sent wave if the source of the wave were moving away from the receiver, right? Now, so that's so we see that with sound, and we practice it with sound, like in the extra credit part of the test. But then the big punchline of all of this is Young's two-slit experiment, which I know you only briefly talked about. And honestly, I might or might not even remove that question from the test because I know you only briefly talked about it. But let me briefly remind you. In Young's two-slit experiment, we find that even light can behave like a wave. Even light apparently travels with crests and troughs that apparently can cancel each other out the way that crests and troughs of a transverse string wave can cancel each other out, or the way that crests and troughs of a sound wave can cancel each other out. In Young's two-slit experiment, he shot light through two slits, and on the screen on the other side, in many, many places, in alternating spots on the screen on the other side, in places where you'd think you'd get light from one slit plus light from another slit, in a lot of places, he got darkness. Now that makes no sense if light was coming, if we were sending a whole bunch of little light particles through one slit and a whole bunch more light particles through another slit, then everywhere on the other side, you'd get light plus light. You get, anywhere on the other side, you get light particles from one slit combining with light particles from another slit. You get like a lot of light, like everywhere you looked, right? Or put even another way, if you just sent light through one slit, you get a bunch of light on the other side. If you opened up another slit for light to go through, you get that much more light. If light were made of little particles, you get lots of brightness all over the screen on the other side. But Young found a pattern of alternating bands of light and darkness, light and darkness, light and darkness. How could that be? That makes no sense if light was going through those slits in the form of little light balls. If light was traveling through in the form of waves, the way sound does, if light were going through in crests and troughs, then you could imagine how in certain spots, crests would be coming in from one slit at the same moment that troughs, or like all crests would be coming in from one slit at the same moment that a trough would be coming in from another slit, and the crest and the trough would cancel each other out and you get nothing, i.e. darkness. And that's what happens in Young's two-slit experiment. I mean, this is just a brief overview, and I know we have like 7 minutes, but I'm just trying to say the purpose of that experiment, or what we get from it, is, oh my God. Actually, and I'm gonna actually get, sorry, just for our last 7 minutes, I'm gonna, okay, hold on. Well, yeah, okay. In Young's two-slit experiment, on the screen across from two slits through which light was being sent, we get alternating bands of light and darkness. That makes no sense unless we're willing to believe that light travels in the form of pulsing ripples through a medium with crests and troughs that can potentially cancel out, sometimes reinforce each other and make bright spots, but sometimes cancel out and make dark spots. So from Young's two-slit experiment, we say, oh, light can travel like a wave. And the light from stars that travels towards us evidently can travel as a wave. But then if that's the case, that light, and I know we have 6 minutes left, if light can travel at us as a wave, then the fact that we receive light at lower frequencies from stars than the frequencies that would be measured in the star frame of reference, the fact that we get light from stars that seems to measure one frequency on Earth, but would seem to measure a different frequency in the star frame of reference, says to us, oh my God, the light must be undergoing a Doppler effect, a Doppler shift. The fact that the light is lower frequency, i.e. redder, when we measure it, then it should be, according to the chemical composition of the star, when the star would measure it, must mean that the stars are moving away from us. Just like if we got a sound from an ambulance and we received a sound that was lower frequency, lower pitch than what the ambulance measured it to be, we would infer, oh, that's because the ambulance is moving away from us. Sorry, I'm just trying to turn off. Okay. We get starlight and we have 5 minutes. That's perfect for me to just put this all together one last final time. The starlight that we measure from typical stars, when we measure its frequency on Earth, at Earth, we get frequency numbers that are lower, that are closer to red than the frequency numbers we get when we just look directly at the chemical composition of the star, i.e. when we just look at what the light would be or should be, or it seems like it is in the frame of reference of the star. Light is more to the left of the rainbow as it is measured by Earth than it is as measured by the typical star. So from that, we infer that stars are moving away from us as they sent this light out. And I'm saying this qualitatively right here in this context at the end of the year, but just like with the Doppler effect problem that you practice for extra credit, you can see we can run these numbers very precisely. And from the differing frequencies, we can infer very specific velocities. Like in the Doppler effect problem that you practice for extra credit, you're given the velocity, you figure out the frequency. In outer space, we get the frequencies and measure them, and from that, we infer the velocities. That's where we got Hubble's law from. Hubble's law Hubble took a whole bunch of data from a whole bunch of different stars at different known distances and calculated their apparent receding velocities according to their Doppler redshifts and put together a whole map and relation and found, oh my God, the farther away stars are, the faster they seem to be moving away from us. The universe is expanding. Now, why? I mean, that's the why. We believe the universe is expanding and that it all started from a Big Bang because we believe that light coming to us from stars is coming at us with frequencies that are lower than the frequencies with which it left the stars, so to speak. The one piece that I have 3 minutes that I just want to throw in at you, the one piece that is like sort of that remains undiscussed in all of this, or the one dot that I still have to connect, you might say is, if you're really following this, okay, wait, if light is a wave, like if light is a wave, as we do say, at least according to Young's two-slit experiment, if light is a wave, and if all waves are ripples in or through media, right? If we've been saying this whole course that like sound is immaterial, it's a phenomenon. Sound is not a thing, it's a ripple through a bunch of things. In the case of sound, the bunch of oscillating things are called air molecules. The collection of the oscillating air molecules together makes the medium through which the sound pulses, propagates, ripples. If you take away the sound, then if you take away the air, you better put something else in like water or guitar string or something. You got to have a medium for the pulses to pulse through. If you literally take away the entire medium and just have outer space, nothing, vacuum, space, you can't send a sound ripple through it. So in the 2 minutes I have left, you might be asking yourself, and I'm about to just say something I think is interesting. That's just the right way to close the course. If this excites you, great, take more physics. If it bums you out, don't worry. You're not going to be, it's not a question on the exam what I'm about to say, but in the 1 minute that I have left, I just want to address the possible question on your mind of, wait a minute, if light is a wave, and if a wave is a ripple or a pulse through some sort of medium, if all waves require some sort of collection of oscillating things for the propagation to travel through, then you might say, what is light traveling through? If light is a ripple and it can ripple through outer space from stars to Earth, what is the medium for that ripple? The medium, the thing through which light pulses, is electric fields. That's why we studied electric fields. Electric fields exist in the universe. They exist everywhere. An electric field is, oh, cool. Yeah, cool. And I know we're just about done. I'm just wrapping this up. Again, you're not going to get a question on this, but I just want you to see how all the material comes together, ideally, at least in the universe. Right? Oh, cool. Okay, so and I know we're just about done, but let me just say this in one sentence as clearly as I can. Okay, remember that an electric field, Like the minute any charge or any object exists in the world, then the information of its existence exists everywhere in the world, right? There's a vector everywhere in space that indicates how big that charge is and where it is, right? And so the field is the information of an object that exists everywhere through space. If an object moves its position, then the information of its position has to change everywhere in space. Like we said about gravity like weeks ago, right? Like if anything ever changes its position, then all the vectors, all of the lines indicate the electric field of it everywhere in space has to adjust. If you picture the electric field to be this big forest of arrows everywhere in space, then the minute I move a charge anywhere, all the arrows have to adjust, right? How do they do that? The ripple that goes through and changes all the arrows, the ripple of the update of the information in the electric field, that's what light is. Light is a ripple through a medium of information. All waves are immaterial ripples through media. Light is an immaterial ripple through a medium that is already immaterial. Fields are the set of information of everything that's in the universe. When anything changes in the field, that change, that update ripples through the field at the speed of light as an electromagnetic wave known as light. Light is updates in the electromagnetic fields that exist everywhere in space. And that's why the speed of light is the same, no matter what you do in space, because you can't move that medium. That medium is everywhere in space. That's the course. That's the point of the course. If you appreciate that, I mean, if you get that, great. If you don't worry, it won't screw up your final exam. I think you're all very ready for the final exam. I think it's been a great pleasure teaching you all, knowing you all. I will stay in touch with me if you want letters of recommendation or anything like that, or further physics inquiries. But I hope COVID gets none of you, and I hope you prevail in the universe. But we're done. I'll stay for 1 second if there's any questions. But thank you guys very much. And I will post all the details about the final. I will post them more clearly. But yes, great. Oh, cool. Oh, cool. Thank you very much. I'm looking to turn this up. Thank you. Awesome.
You're the best. I love helping you.
Oh my God, that was good. That was my Google. Okay, sorry. Thank you guys. Seriously, I'm turning off the recording.